There are multiple ways to solve this optimization problem that constitutes different methods in reinforcement learning. But for the sake of this particular discussion, we will look at one of the popular ways of solving this optimization problem, that is given by the policy gradient optimization. Now, the idea is the following. Suppose the policy that we are optimizing over can be represented using differentiable functions such as neural networks. So one example can be the particular case that we are considering, where the policy is represented using transformer kind of architectures, which is a language model. In such cases, this optimization problem can be solved using the usual stochastic gradient methods. Now, to do that, one should obtain the gradient of this particular objective function, because the gradient descent would say that you take the gradient steps in updating the particular policy. So this is the learning rate, and one would need the gradient of this particular objective function. Now this is the policy updating using gradient descent. Now this can be done only if we can obtain the gradient of the objective function with respect to the parameters of the policy theta, right? So to do that, we'll have to look at what is called as the policy gradient theorem. That is a very nice, powerful result that would enable us to find the gradient of the objective function that we would need to solve the above stated optimization problem. Now let us look at what the policy gradient theorem entails. So what we need is, we need to compute, we need to obtain the gradient of the following objective function. Gradient of the following objective function. What is the objective function that we have? We know that the objective function that we have is the expected discounted return R tau, where the expectation is with respect to tau coming from p theta. So this is the objective function that we have. Now let us compute the gradient of this objective function with respect to theta. So this is what we need, right? So let us write that down. So this is the gradient of the expectation. Expectation is given by p theta of tau times R tau, where this is with respect to tau, which is the trajectory. Okay. Now we know that the gradient is a linear operator, so we can push that gradient inside the integral. So we have gradient of p theta tau times R tau d tau. Okay. Now we need to find the gradient of this particular term p theta tau, because R tau is independent of theta. So now what is this given by? Let us first write this gradient using what is called as the log derivative trick, where we express this as p theta tau times the gradient of the log of p theta tau. Why is this true? This is simply the famous log derivative trick, where if you take the gradient of log of a function, then it is given by 1 by the function times the gradient of the function, which the 1 by function and this function cancels out, and what will remain is the gradient of the function, right? So it is very easy to verify. Therefore, one can write, therefore, we have the gradient of the objective function j theta now is given by integral of p tau p theta tau times the gradient of log of p theta tau times the expected return times d tau. Okay, so now what we need, let us look at the derivative of, consider this particular term, which is the gradient of log of p theta of tau. What is this given by? So we have the expression for p theta. We know that we have p theta of tau to be equal to rho of S naught. We had just defined this using the product rule, right? So p rho of S naught times the product of t is 0 to infinity. We have pi theta of at given st times p of st plus 1 given st and at. So this is the definition of p theta. Therefore, the derivative of log of p theta of tau is equal to the gradient, I can write it as the sum t equal to 0 to infinity log of gradient of log of pi theta at given st. So why is this the case? So what we have is that we need to take the log of this. When you take the log of this, we have log of rho of S naught. This is independent of theta. Therefore, it cancels out when you take the gradient. The other term, which is p of st plus 1 given st and at, is also independent of theta, which is the transition kernel is independent of policy, and therefore that cancels away. So what remains is the term that involves the policy, and because there is a product here and we are taking a logarithm, that would get converted into a sum and we can put the gradient inside. Therefore, the derivative of log of p theta of tau is simply the sum from t equal to 0 to infinity. We have the gradient of log of pi theta at given st, and the derivative is with respect to theta. Now putting this back, we have the gradient of the objective function is simply given by integral p theta of tau times t equal to 0 to infinity gradient of log of pi theta at given st. I'm just rewriting these terms. Look at this. So this is there was p theta of tau, and there's the gradient of log of p theta of tau, which we wrote in terms of the policy, and we have the other term that we have here is r tau times d tau. Okay. Now this can be written as an expectation. We have, this is the expectation of t equal to 0 to infinity log of pi theta at given st times the return, and this expectation is with respect to tau as it is coming from p theta. So this is the most fundamental form of what is called as the policy gradient theorem, where we say that the gradient of the objective function that we use to update the policy is given by this particular expectation. So this is called the policy gradient theorem. Now, as we discussed earlier, what we can do is one can use the gradient descent, the usual gradient descent method, to maximize this particular policy, and we now have uh, an expression for the gradient of the objective function that we have. So this constitutes the foundational method of policy gradient method based optimization function object optimization procedures to obtain an optimal policy in the reinforcement learning paradigm. Now, what we will do next is that we will improvise this. This estimate of the gradient is known to be very noisy, and there are ways to reduce the variance of this particular estimate. We will see those ways of reducing the variance of this estimate, and then we will connect the primary goal that we started with, which is alignment of the language models, to this particular policy gradient optimization method, and close the loop in finding out how would one use these results in aligning the language models that are trained in a completely unsupervised way. Another observation in the particular equation that we just derived is that this expression applies the same total return R tau to all steps, all time steps t, regardless of when the action was actually taken. Right? So we have this R tau here that would apply the exact same return at all time steps. Now we can make it more efficient by define another quantity RT, which is called the go-to reward or return from T. Write this as, this is just change of the time index over k times reward that is computed at time s t plus k and action t plus k. With this, we have R tau to be equal to just R naught, okay, and we can rewrite the gradient of the objective function using this RT now. So here the gradient is equivalently written as gradient of j theta is expectation with respect to tau. We have the sum from t equal to 0 to infinity, the gradient of the log of the policy, and what we multiply here is not R tau but RT, which is the reward that we have computed from time t to infinity at every time t. So instead of computing it from 0 to infinity at every time step, we compute it from t to infinity, right? So this is the form that is typically used. We also said that this particular form that is used has a lot of variance. To reduce the variance, what is done is to reduce the variance of the above estimate, the variance of the above gradient estimator a baseline function, call it as b of st, which only depends on state, is subtracted from the return. Is subtracted from the return. So it can be shown that this does not alter the expected value, but it reduces the variance. I'll skip that proof. So therefore now the new gradient estimate with the baseline subtracted will have this particular form. This expected value of the sum of log of policy. Now here instead of RT, what we have is RT minus B of ST, which is called as the baseline, which is now subtracted from the return t equal to 0 to infinity, and this is expectation is with respect to p tau. Okay, so this is the baseline subtracted version of the gradient. Now there are multiple choices that have been made in several algorithms in the literature. One of the famous choices that is made for the baseline function b of st can be taken to be what is called as the value function v pi of st, which is defined as the value function. So this is one of the choices that is made for the baseline, and it has been shown to be very efficient in terms of computation of this particular gradient. Now let us define what this value function is and see what the final form of the gradient of the objective would look like. Now let us define the value function as follows. The value function as follows. So we have v pi of st denoted by this as the expectation of the discounted reward given that the agent has started at state st at time t equal to 0. So this is this expectation with respect to policy. So what is this? This is the expected return that we have gotten by enacting the policy from the initial state being equal to st. So this is the definition of the value function. Okay, now there is another cognate function of this, which is also called the q function, or also called as the action value function, which is defined as follows. The q function is denoted by q pi st comma at. This is defined in a very similar way to the value function. This is expected value of the discounted return, rather discounted reward, when the policy is executed by taking the initial state to be st and the initial action to be at. Right. So now what is done is that we have ensured that the agent starts at an initial state of st and takes one particular action, initial action, which is at. Now the question that we are asking is, given that we have started at st and taken the action at time t equal to 0, what is the expected reward or discounted reward that we are getting? So this is called the q function. So we have both the value function and the q function defined this way. Okay. Now there is another function that is defined, which is called the advantage function. Which is simply given by the difference between the q function and the value function. Now, this can be interpreted as what is the advantage that, sorry, this is v of s, value function is a function of state. Okay. So what is the advantage or the extra reward that one has obtained by starting at the particular action A? Now look at this. V is telling you what is the expected reward that we get by starting at state S. So Q is telling us what is the expected reward that we would get by starting at state S and taking the action A. If we take the difference between these two, what we would get is the advantage, so to speak, that we are advantaging the reward, the extra advantage in the reward that we are getting by not only starting the trajectory at state S, but by also taking the action A at time t equal to 0. This is called the advantage function. Okay. Functions of the value function, q function and the advantage function, in writing the expression that we need in a more compact form, what we need to recall, what we need to compute is the difference between the go to reward and the value function v pi. There's a nice result that would aid us to compute this in a compact form. The claim is that the difference between the go to reward and the value function that appears in the gradient of the policy is an unbiased estimator of the advantage function. So this is the claim. Let me repeat. The claim is that the difference between the go to reward and the value function is an unbiased estimator of the advantage function that we just defined. How do we show that? So consider the expectation of this particular term that we are interested in conditioned on the state st and the action at. We just split the expectation and show that the value function will just come out and the expectation will just give the exact same value. Now we have the expectation of the go to reward conditioned on st and at, and this by definition is nothing but the q function. Now the second term that we have here is the value function. Therefore the conditional expectation of the go to reward and the value function conditioned on st and at is nothing but the advantage function. Okay. Now what did we just show? We just showed that the expected value of this difference is equal to the advantage function. Now if we just take rt minus v pi of st, it's very easy to note that this is a single sample estimate of the expectation that we have here, right? So if we just take one sample from the underlying distribution, then what happens is that you can take that as a single sample estimate of the expectation. Now this becomes a single sample estimator for the advantage function, right? Therefore the claim that we just said is proved that the difference between the go to reward and the value function is a single sample unbiased estimator of the advantage function because of these three simple steps that we just showed. Therefore, coming back to what we are interested in, so we wanted to get the gradient of the objective function and we showed that it is given by this particular expression, and the baseline was subtracted from the go to reward to make it to reduce the variance of this expression. And the baseline, one of the famous choices for the baseline was the value function, which makes it the difference between the go to reward and the value function. And we just showed that the difference between the go to reward and the value function is a single sample unbiased estimator for the advantage function, right? Therefore the final expression for the gradient of the objective function that we need in policy gradient theorem is given by this particular expression, where we have the sum of the derivative of log of the policy multiplied by the advantage function, and this is also parameterized by theta, right? So this is the expression that is used in most of the state-of-the-art algorithms, policy gradient-based algorithms that are used for alignment of language models. Now there are two questions that we need to answer here. Is that how would one use these results in the setting of an autoregressive language model, and two, how the advantage function is computed in practice. Okay. Now advantage function is computed in practice using a parametric reward model that will be trained. So we will talk about training the parametric reward model later in the course. Now once we have a parametric reward model that is trained, there are several methods such as generalized advantage function estimator or GAEs that can be used to trivially compute the advantage function. The other important question, which is how would one cast an autoregressive based large language model in this particular form of reinforcement learning, is something that we would just see.